Welcome to Breadboarding. In the previous video we used a basic LSTTL inverter gate and we did some experiments to look at the voltages at where the various logic levels switched. So we're normally talking about the logic levels of true and false, 1 and 0, or 0 and 5 volts. But in fact what we found was that the voltage in which it switched from the high to low value, in our particular case during our test, was about 2.2 volts. Now this is actually underneath the guaranteed minimum output voltage of 2.4 volts, but it was a little bit above the voltage in the data sheets that says that it should count high as anything over 2 volts. And we also found as well that when we looked at a Schmidt trigger that in fact there were 2 threshold voltages, so that if we had a fluctuating signal then we wouldn't end up with the output switching at random. So in this video we're going to be looking at the AND, OR, exclusive OR and buffer logic gates, and this is video 8 in the How to Use Breadboards and Retro Digital Electronics series. So in the previous video, video number 6, which will be a link at the top here if you didn't see that, or at the end of the video there will be a playlist so you can actually go through the whole series if you've missed earlier videos. And in this video we're going to be covering the AND gate, the OR gate, the exclusive OR gate and buffer gates. Now I have briefly covered these in earlier videos. I will be going through each one of these in turn, and these are the typical symbols that we use in schematic diagrams for each of the types of gates. And in the next video we'll be looking at the inverted versions of these gates, the NAND, NOR and exclusive NOR gates. So the AND gate is probably the easiest one to understand. It's a very simple, if we have 2 inputs A and B and an output Y, then the only time we get an output of 1 or true coming out of here is when both A and B are 1. So the truth table here just shows us what we get for the different values of A and B. So you can see here that we get 0 coming out for all combinations unless both A and B are 1. And the symbol in here, this is the keycad symbol for an AND gate, but again you can see that apart from it being yellow then there wasn't much difference. Now these are the different types of AND gates that you can actually get, and these are the different chip layouts. This quadruple 2-input positive AND gate, so this is probably the typical chip that we would actually use if we were needing to use an AND gate, and we can see here this is the 74LS08. Now if we just have a quick look at the current data sheet for this chip, so this has come off the Texas Instruments website just earlier today. So we can see up here we've got multiple chips, so the 54 series is kind of the military spec, but the one that we're interested in is the 74LS08. Now what you'll see here is that the chip layout here shows us that we've got the gate 1, 2, 3 and 4, A, B and output Y, but that's not really very useful, and I certainly find it a lot easier to look at these labels with the diagram of the actual circuits on there. And you can see, although it does give you the logical diagram for the chip there, that the labels on here aren't particularly useful. Now you'll notice that the slide I showed earlier has sort of proper layouts, and in fact if we go to this TI Digital Logic Pocket Data Book, this I think is still available from the TI website. I'll include the link down below in the description. It's from 2007, but this has a huge amount of data in it. It's about 800 pages, so we're just going to skip to the bit that has the diagrams in. So I think that's about page about 166, I think it was. So you'll see there's a lot of information here, but this section here has sort of graphical chip layouts, which I think are far easier to use and are much more like the chip labels that we showed in the previous video and the ones that Grant Searle had done in particular, which are quite nice to use. So just make sure we can scroll around here. Right. So you can see here we've got various chip layouts, and in fact the 08 one that we were looking at I think is down on this page here. So you can see that I've taken all of the chip layouts in fact from this document, and I find that this sort of style of diagram much easier to work with, and it's also what the chip labels will generally have on them as well when we start playing around with them. So recommend that you download the TI Pocket Databook. Certainly makes life a lot easier when looking at these things. And you'll see that in fact for the AND gate, we've got one which has 2 inputs. There's one that has 3 inputs. There's even one that has 4 inputs. I don't believe there's anything with more than 4 inputs. And we've also got one here, when we talked about this a couple of videos ago, that the outputs here normally will a totem pole output, so they'll drive the output high or pull it low. But in fact, with an open collector output, then this will only pull the output signal low. It won't actually do anything on high. So we'd actually have to have a pull-up resistor pulled to 5 volts to actually see any 1 values coming out of this particular gate. But these are particularly useful if you're actually got signals which are shared between a number of chips which are all having to drive the same signal. And it means that you can have multiple outputs all connected together, and only when one of them drives the output low will the logic signal change. And because they don't do anything with the true positive value, then it just relies on the pull-up resistor. So we'll have a look at the open collector outputs perhaps in a later video. But the main thing really about these chips is that we only get a positive 1 output when both the inputs, or all the inputs in this case, so for this 4 input AND gate, it was only when we have 4 1s coming in the inputs here when we'll get a 1 coming out of here. So we're going to have a look at the AND gate in a minute, and we're going to have a play around with that. I say it's very simple, it won't really take very long to do that. Okay, so here's our simple test circuit. So this is the 74LS7408. This is our 4 2-input AND gate, and you can just see the gate that we're going to be testing is pins 1 and 2 are the inputs and pins 3 is the output. The pin 3 output is just going to this green LED with a 330 ohm resistor there, and because the output voltage there is a bit lower than 5 volts, then this can be a little bit lower resistance value. And then I've basically got the blue lead and the red lead, which are the A and the B. I'm just going to connect those to 0 volts or 5 volts, and then these 2 LEDs here just show whether or not we've got a 0 when they're off or a 1 when they're on. And these are using 1K resistors just because this will be connected to 5 volts, so will mean that the brightness of the LEDs is not too great. And then this is just the blue LED, is just the power LED to show that the power is on. So to start with, the 2 leads are not connected, so basically we haven't got anything connected to the input, so we're just going to turn it on. And in fact, you can see that the green LED has actually come on. Now, there's a feature quite often that a lot of TTL logic will have internal pull-up resistors, and so if their inputs are actually left floating, then in fact they will tend to pull up. But obviously, because we haven't got anything connected to these wires in here, then in fact the LEDs are off. So if we just wire these up obviously to 0 volts first of all, then you'll see that the LED goes off as the first one's connected. Obviously, with the truth table that we saw earlier, we would expect that when we have 0 and 0, 0 and 1, 1 and 0, we would get nothing. And then only when both LEDs for A and B are on will we actually get a Y coming out. And if we look at the data sheet, so this is the data sheet for this chip, we can see that in fact for the LS08, there is an actual fact an internal pull-up resistor here. So if we don't have anything connected, then this will probably default to being on, which will enable the output. So we have both of these attached to ground, then we should find that the output LED Y is off. So if we attach the blue one, which is A, to 5 volts, then we should find A turns on, but we still have no output. Then if we do B is on, still no output, but when you have both A and B, then we get A. So very, very simple gate. And just want to make sure that was working okay. So now we'll go on and go back to the OR gate. So one other TI document we looked at in earlier videos, there was the logic guide that showed the different logic families. And in the appendix there, it actually includes a section on the different types of gates. And in fact, when I was looking through this, I noticed that was actually one down the bottom here for the AND gates, the ones that I've already shown you in there. But there was also this 7001. And this is a one I've never come across before. Is this a Schmidt trigger input? And you remember we covered the Schmidt triggers in the previous video. And you can see, in fact, on this diagram here, that each of the inputs has got an inverting Schmidt trigger, but also the little circle there on the input means that it's an inverting input as well. So the net effect is that this is just a Schmidt buffer input into the AND gate. So this is one that I haven't come across before. So sometimes it's always worthwhile reading the documentation, because sometimes you come across things that you weren't aware of, and I'm learning things all the time. So now we're moving on to the OR gate. So again, the OR gate symbol tends to be this curved one. So the AND gate has a sort of a more rounded shape and a vertical sort of line with the inputs here, whereas the OR gate tends to be sort of a point at the front there and curvy. And as the name would suggest, that we get an output from an OR gate if either A or B is true. So the only time we get a 0 out is when A and B are 0, but all other combinations would produce a 1. And this is a symbol in KiCad for the OR gate, again, very similar to above. It's just yellow. Now, there aren't so many OR gates available, and in fact, there's only really one main series OR gate, the 74LS32. You can see this is a 2 input, 1 output, so quad 2 input. Looking at TI databook, then there was actually a 7032 series which had Schmidt trigger inputs as well, so similar to the previous one. But the OR gate obviously is, there aren't many variants of these. There are actually generally far more of the negative NOR and NAND have a wider variety of chips, because they tend to be a bit more useful for reasons that we'll cover in the next video. Now we have the OR gate, so you can see that the symbol there is slightly curved and a pointy sort of end to it. So I'm just going to plug this in. At the moment, both the A and B are connected to 0 volts. So we can see the power's on, but we don't have any output. Now when we connect A to 1, we can see we've got A on, but we also have Y, B on, and we also have Y, and then when both A and B are on, then we also have Y. So that proves our OR logic gate. So we can see that we get the Y output for everything other than 0 and 0. Let's have a look at the exclusive OR gate. So this one is a bit unusual, and you'll see the symbol has this double bar. So it's like an OR gate, but it has this sort of extra bar on here. And the XOR gate takes a little bit of working out what it does, but basically it produces a 0 when both A and B are the same. So if A and B are 0, we get a 0 out. If A and B are 1, we get a 0 out. But if they're different, then we get a 1. So only when one of these is exclusive do we actually get an output here. Again, there aren't many exclusive OR gates. The 74LS86 is a quadruple 2 input, and you can see then with the diagrams there. Now, one of the things about an exclusive OR, it is actually possible to produce an exclusive OR gate using the inverter and AND gates and an OR gate, and there's other combinations of gates that you can use as well. But you can see basically that we've got is 2 AND gates with one of the inputs, A in one case and B in the other case, inverted, and then ORed together. So in fact, to produce this sort of truth table, we can actually use these sort of 5 other gates that we've already covered actually to produce this. So not surprisingly, it's a lot easier to use a chip that already does this for us. But in a lot of cases, in the sort of projects I've been doing, a lot of these gates, we now use programmable logic devices, or PLDs, and we'll be talking about those once we've finished the next video. And there's a whole series on using programmable logic devices. These are chips, a similar sort of size, but we can actually program all the logic rules such that rather than needing 3 or 4 chips, or in this case, rather than needing 3 chips to do this, we could actually program the programmable logic device to actually do the exclusive OR without needing to have any other chips. We could also do things like ANDs, NANDs, NORs and things like that in the same chip without needing to have multiple chips when we perhaps only want one gate. So we'll have a look at the exclusive OR now. Now we have the exclusive OR gate, so it's difficult to see, but you can see that this is an OR symbol with there's an extra line on the inputs of A and B. So we switch this on. You can see the power's on, but we don't have anything output. So the inputs are both A and B are both 0. So if you now make A to be 1, you can see we have A is 1, and we also get an output on Y. We make B 1, and we also get an output. And if we make both A and B 1, then in fact we don't get an output. So if we go back and have a look at the slide. Now we've done the exclusive OR, we're going to have a look at the buffer. Now in the previous video we covered a buffer basically just strengthens the electrical signal really, so whatever comes in comes out. And the diagram that we saw in the previous video, this is the schematic element for a buffer, but in fact if we've got a 3-state or tri-state buffer, what this input here effectively allows us to turn off the output here. And what that means is if we need to have lots of chips all talking to the same bus. So in particular with a microprocessor, the data bus quite often has an awful lot of chips all driving the data bus, whether they're reading or writing to it. But we can only really have one chip writing to the bus at the time. And so when the outputs are disabled, so generally with the circle here, it means that when this input is low, then the output will be enabled. When it's high, then it's disabled. This means that we can have all the different things that we'd have, like RAM, EPROM, floppy disk controllers, hard disk controllers, and video controllers, all talking to the same data bus, but not actually conflicting with each other. But if we have problems when we're looking at the circuits, then sometimes we can find that if our signals controlling these buffers are incorrect, then this is what causes problems when we've got more than one chip trying to drive the buffers. And the one that we're going to be using here is, in fact, this is an ALS series, a 74 ALS 541. Now, the advanced LS series is what we've been using in a lot of these projects, mainly just because it's a little bit, has slightly higher output capabilities and can switch a bit faster, particularly when we're starting to look at using these chips in video controllers and things. Then they're just able to handle the higher frequencies a bit better. Now, the symbol inside this chip here, it's not quite the same as a Schmitt trigger. This just means, I think, a buffer. There's certainly not Schmitt triggers in here, and it did confuse me a little bit when I was first looking at this. I think the Schmitt trigger has sort of the more vertical symbols here. If anyone knows better than I, then please feel free to comment in the comments below. So in fact, in this particular chip, there are 2 active low output enables. So if we only want one output enable, we would just tie one of these to ground or to 0 volts. And so when both of these are low, then the output here will be enabled. Otherwise, then it will be tri-state, so these will just float and won't be driven in any sort of way. And this is the symbol from KiCad. In the diagrams that I use in KiCad, what I've tended to do is to change these layouts. So quite often the chip layouts be arranged logically, so the inputs on the left-hand side and the outputs on the right-hand side. Now, in fact, on this chip, pretty much all of the outputs are on the right-hand side, apart from this sort of G2 select output enable. But what I tend to do is to make sure that the chip layouts actually match the physical chip layout, because it means that then our schematic diagrams can actually then be used as the physical board layout diagrams. And it's just less likely they're going to make mistakes when you see that there's a pin over on this side being wired up, when in fact it's physically over on this side. So you're going to have a look at this buffer, and what I'm going to do in fact is to use a couple of crystal oscillators to actually drive the inputs to the buffer. And what we're going to do is to actually look at what happens to the signals when we start to put these down longer copper tracks. This is our buffer testing circuit. So what I've actually done here, I've taken out the LEDs other than the power LED. What I've got is a crystal oscillator, or it's actually not a crystal oscillator, it's an oscillator package which has a output here, 5 volts, ground there, and the other pin I don't think is connected. And I've found these to be much more reliable for getting oscillators in breadboard circuits, trying to get the crystals and the inverters with the necessary capacitors and resistors oscillating has sometimes been challenging, but these things seem to work every time. Basically, the output is connected to the oscilloscope, so the yellow trace is actually the oscillator output. Then it's going into the left-hand side of the buffer, and then I've connected the oscilloscope to the output. And at the moment it's not connected to anything. And then once we've looked at that, what I'll do is got this strip board here. So this is a strip board I'm starting to make for the next project, and it has rows of copper strips down on the underside of this, just like I used previously. And what I've got up this end is a number of connectors here that one thing I'm going to experiment with is adding some termination resistors at the end here at some point in time. We're not going to do that for the moment. All we're going to do is to see what actually happens when we try and shove various oscillator outputs down the bus here. And also I've got a variety of crystal frequencies. So the one here is about 3.68 megahertz, which is the frequency which tend to be used for driving serial ports. So this will do frequencies such as 115.2 kilohertz all the way down to about 9600 baud. This is just under about 4 megahertz. Then I've got 8 megahertz, 16 megahertz, 25 megahertz, which is the VGA dot clock. And I've even got a 40 megahertz one. So we'll see what happens with that one. I'm not expecting that one to be great with this setup, but it's just out of interest. So what we'll do is to just zoom in so you can see what the circuit looks like. So you can see we've got our crystal here with the output. The output's just going into A0. What I tend to do with these chip labels, by default, a lot of the data sheets start at 1 and go to 8. However, when you're dealing with a lot of digital signals with microprocessors, since we're always dealing with 0 indexed, what I tend to do with these chip labels is start them at 0. And sometimes also, depending on the breadboard layout, I might also have it going from 7 down to 0. So I have two layouts for the chip labels, both starting at 0, but one has 0 at the top and the other one would have 7 going down to 0. Now these other inputs are not connected at the moment, but for the moment we're just going to be looking at this one output here. So let's just switch back to the view that allows us to see the oscilloscope output as well at the same time. Okay, so there's nothing on the oscilloscope at the moment, so let's just turn it on. Okay, so perhaps if I just go to full screen just for the moment so we can see this. So you can see that the yellow trace is the output of the oscillator, and you can see there's a bit of ringing as this sort of settles, and that the frequency here is 3.69 megahertz, and then this is the output from the buffer. Now the output of the oscillator here is almost 5 volts, so each one of these is 1 volt, and you can see the output from the buffer there is just under 4 volts. It's about 3.8 volts, and that's what we would expect with the TTL. We wouldn't expect it to necessarily get all the way up to 5 volts. So that looks fairly clean, apart from this sort of ringing. It's not too bad. The edges at the end are fairly okay. Now I will be looking in one of the later videos when we're looking at more buffers and latches. We'll look to see if we can actually minimize this sort of ringing during that video as well. But I need to do some more research into it first. Okay, so I'm just going to now hook this up to the tracks here. So I was going to use yellow for 0 volts and orange for the signal. Then I'm going to leave this on the output there, but I'm going to move this probe and I'm going to put this actually down the end here. So what I'm going to do is the 0 volts is on the yellow, which is on the left hand side, and I shall hook up this probe and we shall see what the difference in the signal is by the time it's actually gone through these wires and gone all the way down the bus. So now let's just switch that on. Okay, so that's quite interesting. I think you can see there's quite a large undershoot there on the yellow signal, and the yellow signal is that is down at the bus at the bottom here. So if we just switch it back to the main screen and we can see that a bit better. So you'll see here that the blue signal is the one coming out of the gate directly, but then when it's gone over the jumper cables onto our bus rails and things, then in fact we've actually got quite an undershoot here, and in fact this is probably about 1.5 volts undershoot, and then it oscillates a little bit before it settles down. Now this might be something that we would have to worry about, because a lot of the chips will allow a certain amount of undershoot, -1 volt for example, but I'm not sure whether -1.5 volts is going to do something any good. So let's just switch back to the other view. Now what I'm going to do is to swap out the 4 MHz one, and I'm going to try the 8 MHz by switching that on. And that's similar, obviously a higher frequency. There's still an undershoot probably of about 1.5 volts there. But the actual signal, apart from the oscillation on the rising edge there, then that looks reasonable. Now I'll do 16 MHz. Now 16 MHz is the frequency at which some of the clock signals on the Compact Desk Pro 386 works at, which is one of the projects I'm looking at the moment. So we can now see, if we just increase the resolution on the... You can see that in fact at 16 MHz things are beginning to round out a bit now, and that certainly the blue signal is still around 0 volts. It is going slightly below 0 volts, but that the bus signal is still sort of undershooting by a fair old way. Now let's try 25 MHz. So this is the frequency that we use for the video controller dot clocks, because this is the frequency needed for a VGA video output at 640 by 480. Okay, so it's still undershooting by probably a little bit more now. We're almost up to about -1.8 volts here, in fact. But the output from the output of the chip is still sort of going to 0 volts. Then finally, as a bit of a test, let's see what happens with 40 MHz. Now I wouldn't expect 40 MHz to work very well, but we'll just see whether 40 MHz will actually work over through these chips and on the bus rails. Okay, so it is, but however, the undershoot now over the bus rails is almost 2.3 volts, I would say. Now that certainly is not good news for logic chips. You probably wouldn't want to feed that in. It's only for a few nanoseconds that it's occurring, but even so, it's probably not great. So this is one of the problems with driving buses, in particular, these sorts of parallel strips and the inductance and things that you get from the various bits of wire and things. So I'm going to look into ways of mitigating and minimizing that. I think what this does indicate, though, is we probably don't want to put sort of 25 to 40 MHz signals over long bus rails and things. However, when we're down at the sort of 4 to 8 MHz, then it wasn't quite so bad. But that's just showing the output here for the buffer here. I just move the oscilloscope trace over so we can actually see the rest of the circuit there. So I've switched this back to the first oscillator that we're using because the output is just a little bit cleaner. You can still see there's quite a bit of oscillation ringing as the edge is rising, and also then when it's falling, and this is almost certainly caused by inductance. So I'll be looking into this over the coming weeks, and I suspect that if we add some form of series resistor for the output, then that will reduce it somewhat, and there might be some other pull up and pull down resistors we can add to the bus rails. If we add the termination resistors down the end here, we may be able to reduce this somewhat. But it's interesting to look at this just from the point of view, if this was going on a live project, then you could end up with all sorts of strange things going on. So that's all I was going to do for today. And in the next video, we're going to be looking at the NAND NOR and exclusive NOR. So these are the inverse of these gates here. So we've covered the AND OR, exclusive OR and buffer gates, and we've also seen that when we shove higher frequency signals down the bus rails here, then in fact that there's not an inconsiderable amount of ringing and overshoot on some of the signals. And in fact, when we were dealing with the 40 MHz signal, then in fact the overshoot here for 40 MHz was getting to over -2 volts. So that was getting to a situation where it might actually start to cause some damage, chips being connected to it. But in reality, the frequencies of address and data buses is probably going to be more around the sort of 4 megahertz signals and lower, just because of the way how the bus cycles work. Even with a 16 megahertz clock, then we're likely to need multiple clock cycles to actually do memory reads, memory writes, and so the frequency on the bus and address rails is likely to be less than certainly 8 megahertz. So if you don't want to miss out on future videos, then please hit subscribe. And if you found the content interesting and useful, please hit like. It just helps to make the videos available to more people. Thanks for watching.